kind introduction, David, and thank you for the invitation to talk here. It's a great pleasure to talk about climate change, which I think is one of the biggest issues that's facing us today. And it's also got some really good science behind it. And I think sometimes in schools you hear a lot about climate and environment and things as if it's a sort of soft subject. And there's an awful lot of applications and policy on it, of course, but there's also good science. And I'm looking around to see if there's any students here who might be interested in doing atmospheric physics, because no, it's a lot of good science in there. So here's a graph. I'm going to show you a lot of graphs. This one is a time series of the last 150 odd years of temperature. It's global average temperature difference to what it was around the year 2000 or something like that. And there's 6 or 7 different reconstructions of temperature here. And you can see they're sort of wiggling around, and it goes up here and it flattens off a bit and it's gone up again here. And if we look and see the overall range of that, we're now 1 degree warmer globally averaged than we were at the beginning of that 19th century. And this is what's of course become known as global warming. And I hope to try and tell you a little bit today about what that means and why 1 degree does matter and what it means over the globe. So I'll do a little bit about the factors influencing the climate and the evidence. I'll do a bit of physics, but not a lot, don't worry. The difference between weather and climate, and then think about what might happen in the future, which involves using climate models, which are big computer models, to do these forecasts. And then looking at ways which we could perhaps mitigate against the global warming that's going on. So, yeah, I'm a physicist, I'm not a great art person, so this graphic is a little bit crass, I'm sorry. And here's a not-to-scale picture of the Earth and the Sun. And all the energy driving the climate system comes from the Sun. So there's a tiny little bit of energy coming out of the centre of the Earth, but it's minuscule compared to the energy that's coming from the Sun. So all the energy is coming from the Sun, then the Earth gets hot, and it emits radiation to space. And if everything's in equilibrium on a global annual average, you can quite easily work out what the temperature is if you know the incoming solar radiation, and you can work it out, minus 18 degrees Celsius. So you say, oh, hang on a minute, she says it's very easy, and look, she's got the wrong answer. That is because when you work out that balancing temperature, that is the effective temperature of the radiation that's leaving. And to understand the temperature of the surface, we need to go a little bit into the atmosphere more deeply. So here's a bit of a fussy diagram. It's not as complex as it looks. Here's the yellow radiation coming in from the Sun. Some of it's immediately reflected back to space. And about half of it gets absorbed by the surface, and that warms the surface. The surface emits heat radiation, but about 90% of that is absorbed by the atmosphere, mainly by greenhouse gases and also by clouds. And then the gas, it is material, it is molecules, it gets hot, it radiates both upwards and downwards. So now we've got more radiation coming into the surface, heating the surface, and that's why the surface temperature is about 30 degrees warmer than the minus 18 that you get if you just look at the top of the atmosphere balance. So this is what's known as the greenhouse effect. It's been well understood for well over a century. And it's a result of the fact, just as the composition of the atmosphere allows half of the solar radiation through to the surface, but allows only 10% of the radiation directly back to space. So the atmosphere here is acting like a sort of blanket. And a change in any of these streams, because there's lots of little things mentioned on this picture, changing any of these things will affect the surface temperature, and in particular changes in the greenhouse gas concentrations. So I've said that. So what are the gases in the atmosphere? The most popular ones, of course, are nitrogen and oxygen, but they are essentially ineffective in this context of radiation balance, so we want to look at the greenhouse gases. The most important greenhouse gas is water vapour, which of course is in the atmosphere, very variable, from 0 to 4%. But the thing about water vapour is you can't put more and more and more of it into the atmosphere and it stays there. If you've got a certain temperature, it'll just fall out again. That's a basic physics equation. So you can try and put more in, but it'll just come out again. But carbon dioxide, which is the next most important greenhouse gas. You can carry on putting it more and more and more, it'll just stay there. In fact, its lifetime's about 200 odd years, so it stays there effectively without coming out again on human timescales. So, carbon dioxide is at a concentration of 0.04%. Doesn't sound like very much, but let's see how it's been changing. And what I'm going to do here is lots of graphs. I love graphs. And each of these panels is going to be time and carbon dioxide concentration. And you can see over here I've got the 0.04%, which is today's concentration. And if you go hundreds of millions of years ago, you see that the concentrations were far, far higher than they are today. Far, far higher. But what you've got to think now is actually that was when the Earth was in a completely different state. I don't know if there's any sort of geologists here who can tell more about that than me, but the continents weren't in the same place. Certainly the composition of the atmosphere was completely different, and life on Earth, we haven't even had the first primates, and they appeared a few million years ago. So it was a completely different setup then. Now let's look at what happens more recently. This now is in hundreds of thousands of years, and you can see the 0.04 is up the top there now. And over those hundreds of thousands of years, it's gone up and down between about 290 and 180, but it's never been above that value, and nothing like what it is at the moment. And modern humans didn't appear until 200,000 years ago, so you can see it is a normal sort of concentration for us. And if we look, this is 10,000 years, it's pretty flat at about 270 parts per million. So part per million is a molecule per million. And then if we go over 1,000 years, you see it's pretty flat all the way along here until you just get to the end of this little red whoopsie at the end there. And that's that red whoopsie. And you can see that's over the last 50 years. And these are measurements from Hawaii. This is very, very clean air. It's not directly coming from a factory or anything like that. And carbon dioxide is well mixed in the atmosphere, so this is a representation of the global concentration of CO2. And we know it's coming from human activity and not anywhere else for several reasons. The two most obvious ones are, firstly, it's low in carbon-14 isotope. Now, fossil fuels, of course, are very, very old. And so the carbon-14 has reduced, it's decayed, the higher isotope of carbon has decayed, and there's less carbon-14 in fossil fuels than there is generally in life and things like that. So the atmosphere is depleted in carbon-14, so that's because of the burning of fossil fuels. And a related effect is that the actual oxygen content of the atmosphere, only by tiny fractions at the moment, but it's measurable, is depleting. So we're burning the carbon, we're taking out the oxygen is very, very slightly going down. So this increase is due to human activity, and it's completely unusual. This last picture is just the last few years of that. There's an annual cycle due to photosynthesis of plants more in one hemisphere than another. And the highest that we've measured is May this year, now at about 415 parts per million. So you can see this is way off the top of any of these three plots. So I hope I've showed you that it's unnaturally high. But how can only 4 molecules in every 10,000 have an effect? You might think, it's too weak to actually do anything. So let's have a little bit more at its physical properties. Now this graph, the red curve, is a spectrum of radiation coming from the Earth's surface. So you'll be well aware that light has a spectrum of going from red light through to blue light. Heat radiation also has a spectrum, and here it's going from these wavelengths, you can see at the top here, low wavelengths to longer wavelengths. And coming out of the surface would be something like that red curve there. But the spiky curve is a spectral flux measured at the top of the atmosphere. And you can see it's less than the red curve, in a very variable sort of way, but particularly this end, and that's associated with water vapour, and this end, and that's associated with water vapour, and then there's other minor constituents you can see here, but this big bite out of the middle is due to carbon dioxide. And if we look now at the difference between those two curves, we can see here. So that the water vapour stops about 70 of these watts per square metre of energy getting out. And the carbon dioxide stops about 25 watts per square metre. going out. And the very interesting physical properties of the gases are such that carbon dioxide just absorbs at places where water vapour doesn't, just so happens. And it also just so happens to be absorbing where the peak of that red curve is at those wavelengths. So it's got a double whammy of being effective. And as I've already said, the oxygen and the nitrogen and the argon are doing absolutely nothing. So the carbon dioxide and the water vapour absorb the energy from the heat from the surface, they get excited, they wobble around, they bash into the oxygen and nitrogen molecules, which then move faster, and that's a higher temperature. So back to this graph again. So I said anything that affects these streams will affect surface temperature. And of course, one thing that might change is the incoming solar radiation. And you do hear some people say sometimes, oh, it's all right, it's all due to the sun. So let's have a look at that. We can look at the Earth's orbit around the sun, and it's actually an ellipse, it's not a circle. And also I should be well aware the axis of the Earth is tilted so that there's a summer hemisphere, which is the southern hemisphere here and there, and a winter hemisphere. So there's two parameters that you can that can vary. One is the ellipticity of the orbit, another one is the tilt of the axis, and the third parameter is the point at which this axis is pointing in towards the centre on the ellipse. So three parameters that can vary, and these three parameters do vary on very, very long timescales, so tens to hundreds of thousands of years. And of course, these variations will affect the amount of radiation received from the sun and where it falls. So clearly, you understand about the seasons, and you can see that the seasons will be different if there's a different tilt. But now we're going to look at the temperatures over hundreds of thousands of years, and you might think, hang on, I've shown you this graph already. I haven't shown you that graph already. What I have shown you is the CO2 graph. And you can see now that they're very similar. And sometimes you'll hear people who you might refer to as climate skeptics or deniers or whatever, wanting to deny that human climate change, saying, oh, it's all right, we've seen it all before, CO2 goes up, temperature goes up, then it comes down again, it's all natural. And of course this, oh dear, I keep pressing the button, this is all natural, absolutely. But what's happening here is this Earth orbital thing changes on a 100,000 year timescale. So all else being equal, that would be a small harmonic curve just coming down here like this. But what happens is when the solar effect gives us a little bit of warming, then you get the release of gases like carbon dioxide and methane from stores under the oceans, in the permafrost and other places. So the carbon dioxide increases, and methane. They're greenhouse gases, that warms the planet more. So temperature goes up, more gases out, more heat, more gases out, more heat, more gases up. It's a positive feedback effect, and that's why that's such a sharp increase. And it only turns around and goes slowly back down again when the solar orbital effect turns off. So this carbon dioxide here is both a result and a cause. It's hand in hand with this temperature effect in perfectly natural cycles. And these are actually ice ages, these cold periods here, and interglacial periods. So, far from being reassuring, we've seen it all before, it's actually quite scary, because what it means is that anything that gives the atmosphere a bit of a push warmwards will get a positive feedback like this on these very long time scales. So more warming due to human activity will give you more CO2, will give you more warming, etc., etc. But this is happening on a much slower time scale than what we've seen recently. So I said that. And this is about the rate of warming. So let's go back again. That's about, if you look at the rate of warming over one of these bases here, it's of order 5 or more degrees, and it takes about 5,000 years. And if we look at the rate of warming on the graph I showed you right at the beginning, it's gone up 1 degree in 100 years approximately. So it's 10 times as fast. So again, this is it's not natural sort of anything else effect. And this is why it's more difficult for ecosystems and everything else to adapt. It's not seen it before. So I said I'd do some physics, and I make no apology, and I'm going to do what you're never meant to do to a non-specialist audience, which is show equations. And I'm not apologising because there may be some young people here who like equations, in addition to which I'm going to show you why I'm showing you the equations, and it's all to do with computer models and that we use for forecasting, so bear with me. Laws of physics in the atmosphere. So you may remember from school days Newton's second law, force is mass times acceleration. And the forces that are acting on air in the atmosphere is gravity, there's the pressure gradient. So if it's high pressure over there and low pressure over there, the air will tend to go that way, try to go that way. Then you've got effects of the Earth's rotation, and you've got frictional drag. And that's the equation. I'll come back to that again. Conservation of mass. So if you've got a volume of air here, what goes in must come out or get squashed. So you can write that like that. Next one, first law of thermodynamics. If you've got some air and you heat it, it'll get hotter or it'll expand. And you can write that like that. And you've got the equation of state, or something like an ideal gas law, which you may remember as PV is RT, but that's another way of writing it like that. So why have I done all that? Because if you write all these down, I'm now colouring the variables. So I've got this U here is the wind, and it's a vector wind. That means it's got three components. It can go east, west, north, south, or up and down. The rho is the density, the P is the pressure, and the T is the temperature. And what we've got here now is essentially 6 equations in 6 unknowns. So you'll be aware of simultaneous equations. You solved them for 2 simultaneous equations. You've got 6 simultaneous equations we can solve. There's various sort of slight things in brackets around this, but never mind. First of all, we have to know this frictional drag and the heating. And then you've got to do the time stepping. But the point of showing this is to show you that it is absolutely basic, lovely, classical physics that you just put into equations and you solve them, and you can create models of the atmosphere and the weather and all the rest of it. So we use these models on a sort of 3D, we set the equations up on a 3D grid, and you step forward in time. And that's essentially weather forecasting, and that's the sort of model that the Met Office use for the forecasts that you see every day. It's also exactly the same model run to forecast the climate over hundreds of years. So you might say, here we are, how can models which are limited skill in predicting the weather over more than about 10 days, clearly we're aware of this, how can we possibly use the same models to predict the climate over centuries? Well, the answer is that weather and climate are not the same thing. So with weather, what we're trying to do is predict what it's going to be like in Highgate next Tuesday at 10 AM, sort of thing. With climate, we wouldn't try and do that. We'd say, what is the average properties of southeast England in winter in 10 years' time, or something like that. So it's a sort of typical values over regions, and you not only get the typical values, you also get a spread of uncertainty, so a sort of, spread of bids that you could think like that. And the climate models are rather good at doing this sort of thing, provided you get the forcings right. So can we explain the shape of this graph? This picture here, the black curve there is the same temperature as I've already shown you. That's the observed temperature curve. And if we use computer models in which we put in increasing greenhouse gases, changes in industrial pollution, so that means not only greenhouse gases come from pollution, but also particulates. So if you've got, say, sulfur dioxide coming from power stations, they turn into little sulfate particles, and they reflect sunshine back to space and cool the planet. That's observed. Or you can have black soot, which absorbs heat and warms the planet. So we put all those stuff in. You can put in changes in land use. So if you deforest a place and it gets more bright surface, that will reflect more sun to space, that will cool the planet. And then we've got the natural things, which are the sun and the volcanoes. So the sun, I've talked about orbital variations, but also the sun does vary in energy output very slightly within an 11-year cycle. You can put in the effect of volcanoes, and if you get a massive volcano, chucks a load of stuff up into the stratosphere and it stays there for a couple of years, again it'll reflect sunshine to space, and it's measured to be actually cooling the planet. Then you've got energy into and out of other parts of the climate system, not just the atmosphere, but into the oceans and the ice and all the rest of it. And finally, and very importantly, you've got this term which is noise. Now the wonderful thing about the climate is that it's such a complex system. It's not just, I've written down the equations very simplistically, but There's all sorts of uncertainty around this. And these coloured curves here are different models and running with these forcing factors. And each of them starting very, very tiny different starting place. So if you didn't quite know, or you've actually got to have the starting places all over the globe, if you didn't quite know what the starting temperatures, etc. over the globe were, you make a slightly different adjustment, it'll do a different evolution. So, the simulations of the models are like this, wiggle, 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 and you might be up there or you might be down there, and of course neither of those is exactly on the black line. But you see, if we run lots of these simulations, the envelope of these coloured curves maps the observed temperatures very clearly. And I can show in a bit further on that, and that's the same picture as I just showed you. And this is the same thing, but now the models, the wiggles, have only got the sun and the volcanoes. They've only got the natural forcing. So we understand the physics of the forcing, and we can show that actually you can't get recent warming without those forcings. This is to make the point that global warming is not the same everywhere. So you can see this map is a 100-year change in temperature, and the average is about 1 degree over the globe. The white areas is where there's not enough data to say. But there's much more warming over continental land masses than there is over the oceans. And very intriguingly, there's some places like over the North Atlantic here where it may even have cooled. And the oceanographers are really quite interested and excited in this as a sort of challenge to understanding. And it's probably due to the fact that when you change the winds, you change the ocean circulations, and there may be more cold water coming up there, and actually it is cooling due to climate change. The other point to be made, of course, is that if you live in different parts of the world, you experience climate change differently. So if you're living somewhere else over here, so you might say you don't really care because it's not really having much effect. But if you're living in Africa where the temperatures are already 30 degrees and you're going up 2 degrees more, you know, it's not fun. You can't carry on like that. So other evidence, I've talked about temperatures, but of course there's a lot of other different measures. This is Arctic summer sea ice, and it comes, it grows in winter and it shrinks in the summer, and you can look at it at the summer minimum, which tends to happen in September. You can have a map here, and that's 1979, and that's 2011. And you can see it's less in 2011, but of course we have to be very careful not to draw conclusions from just 2 data points. But if we now look and see what's happened over the years, you can see that it's just been declining and declining and declining, with wiggles, complex system, etc., etc. And people are placing bets on when it's going to be first 0. And of course the Russians and others are already planning to be sailing ships across here, exploiting minerals and all the rest of it when the ice is not there. So that's a bit of a big deal politically as well as geophysically. In addition to which, there's a sort of climate feedback effect, because if you remove ice, you have a darker surface, which means there's less reflection of the sunshine to space, which means you're getting more radiation in, so you're warming the climate more than you were. It's a sort of positive feedback effect. Sea level rise, you will be aware of. That's a graph of sea level rise over the last 100 years. So it's gone up by about 150 or 200 millimetres at the moment, globally average. Although this figure is being challenged, it may be going up more, but anyway, that's about the minimum of it. I don't want to look at that one. And this is coming from ice melting on land. So that's a picture of Greenland ice cap, and there's a tiny little glacier there which you probably can't see, and that's the glacier. So if you've got sea ice, it's floating on the water. If it melts, it doesn't affect sea level rise because it's like a cube of ice in your drink. You know, it doesn't affect the level of the drink. It just melts and becomes part of the drink. But if you measure ice if you melt ice on land, it melts off and it falls into the water and raises sea level. And if you look at this sea level rise, half of that curve is due to melting land ice, so mainly from Greenland and also the Antarctic ice shelf, more the Antarctic ice shelf. And secondly, due to thermal expansion of the ocean. So if you imagine everything's getting warmer, the oceans are getting warmer. When things get warmer, they expand, and it can't go sideways and it can't go downwards, so it has to come upwards, and that's sea level rise. So half of that's due to thermal expansion. Right, here's my little movie, which may or may not work. We'll give it a go. This is on the context of extremes, so heat waves. And this is it's a histogram showing the distribution of temperatures over the northern hemisphere the average relative to 1951 to 1980. So the average is 0, so most places are around 0. Some places are hotter and some places are cooler. You know, that's what an average means, but you've got a distribution. And what I'm going to show you, if the movie works, is how that distribution shifts year on year from 1950 to more recently. Right. Is it doing anything? It did before? Yes?
Oh, yes, yes.
So, what you've got here is every year you've got a graph, and it's sort of 10-year average, but it's shifting. And you can see it's moving to the right, which is not surprising because we've got global warming, so the average is going to be warming. But I think what this illustrates very starkly is that something that in the original distribution, which is something like that green line, over here was extremely unusual. This is 3 standard deviations, you know, very, very unusual events, and very few places would be warmer than that. That temperature now is actually quite common, and lots of places are now warmer than that. So you can say that a 1 in 1,000 high temperature event in 1950 is now a 1 in 15 event. On the other side of that coin, absolutely, of course, is that there's fewer cold events. So if you live in a place that's cold and you less cold spells, that might be a good thing. So we have to be very careful about not talking about all climate change. Is it inevitably bad? I mean, on average, it's very bad, but you do have to be careful about making statements. So summer 2018 will be essentially normal by summer 2050 in the UK. And that's an example of extreme heat waves. We can do things, similar plots on precipitation, storms and winds and all the rest of it. So if we accept the principal cause of global warming over the past, say, 250 years was increasing concentration of greenhouse gases, if we're going to try and predict the climate in the future, we've also got to predict future CO2 and other factors. Now, you know, I can manage the physics, I can't do economics and predict what's going to happen in all the economies and the social and all the rest of it. But there are people who do, and they set up scenarios of what might happen in the future under various assumptions. Oh, sorry, first of all I should talk about what are greenhouse gases. So this is greenhouse gases, and about 3/4 of the greenhouse gases is carbon dioxide. Human greenhouse gases is carbon dioxide. There's also important contribution from methane, nitrous oxides, and then these fluorocarbons and things like that. And if we look where they're coming from, about 1/4 is coming from electricity and heat, about 1/4 from agriculture, buildings and industry about another 1/4 or so, and then transport accounts for most of the rest. So if you try and predict the future, you've essentially got to predict what all of these sectors are going to do. In what I'm going to show you, it's just going to look at electricity and heat. Now this is a bit, sorry, it's a bit of a complex side, but it's to introduce the Intergovernmental Panel on Climate Change. That is the United Nations body that writes these big fat reports that come out every 6 years or so, which is the state of the art of the climate and climate science. So they construct these representative concentration pathways of the gases into the future about what might happen. And you can see here, this is in the year 2000, the energy composition of energy sources of the world was this: coal, oil, natural gas, and a tiny bit of bioenergy. And then these other scenarios, these representative concentration pathways, RCPs, which are varied assumptions. So this one here has got a lot of bioenergy. This one here has still got a lot of coal and fossils, a bit more solar. This one's got a whacking amount of coal still. It's not giving up on coal at all, or oil. And it's got some bioenergy and actually more renewables as well. These are not, of course, this is not exclusive. These are just 4 sample pathways that you can put into your model to see what happens. So if we look and see the emissions from each of those pathways over the next assumed emissions over 100 years, this one, RCP 2.6, is this green one here, which peaks around 2020 in emissions and then declines to 0 by about 2080. You should note that this work was done in 2014. That's 5 years ago now. I'll come on to changes in a minute. And then these different scenarios have different emissions, whereas the blue one, which is the 8.5 one, is heavy on coal and it's going up and up and up here. That is emissions, but as I've already said, carbon dioxide has a very long lifetime in the atmosphere, so you put it up, it stays there. So emissions doesn't equal concentrations, so we can look and see what happens to the concentrations, and that's what that looks like. So you see that even the green one, which is peaking here and going to zero over here, is slowly coming back. It's still well above 400 in 2100, even with this very extreme activity here. And the one with the heavy-duty stuff, business as usual, is shooting upwards. So those are the scenarios, and what I'm going to do is show you some results from just the green one and the blue one. Oh no, I'm going to show you. I haven't got time to do this, but this is a wonderful website. If you've got time, have a look at this. Global calculator, and you can have wonderful games. And you can say, I'm going to only use non-carbon transport. I'm going to build wonderful buildings. I'm going to become. There's different example pathways here. I was speaking to somebody earlier who's got a daughter who's a vegan. There's one here that the Vegan Society put in. Of course, nobody's eating meat, and everybody's bicycling. I mean, it's great. And you can look and see what the CO2 emissions do and what the temperature does, and how you can avoid it. And you can play games. You know, it's quite instructive. Right, now, so what I was going to do is show you some results of the models. And this is the temperature in response to say the best and the worst. It's neither of those, but never mind, let's call it that. The best and the worst scenarios. This again is from the Intergovernmental Panel report in 2014. And they're all relative to 1990 or something, which is really irritating, because if you want to get back to relative to pre-industrial, you have to add 0.61 to this scale. So this one, which looks like the temperature's sort of flattening off at 1 degree by 2100, is actually, you have to add, so it's more like 1.6 degrees by 2100. And this one, which looks like 4 degrees, is actually more getting on for 5 degrees by 2100. So that's the temperature. Then we can look at other things too. I haven't talked much about precipitation yet. What this plot is showing is, this is temperature across the top here, over the globe, and this is the better scenario, and that's the worse scenario. So of course it's not so hot here as it is there. This one's now, certain places are going up well over 10 degrees, and with greatest warming in the Arctic, interestingly. I didn't show the Arctic in that previous map because there's not enough data yet. This is precipitation. This is all very uncertain if you just use this low scenario. But if you use the heavier scenario, you can see clear signals where there's stronger tropical storms, stronger Indian monsoon, and a much drier Mediterranean in response to the greenhouse gas increases. This is the response of sea level rise, so it's shooting upwards. The thing about this is it carries on going for a very long time, because the heat in the atmosphere and the oceans equilibrates on a very, very long time scale. So sea level rise carries on going for quite a long time after you stop emissions. This is again, I say fun, I mean, perhaps fun's not quite the word. Instructive website you can have a go at, and you can choose your sea level rise and see who's underwater, basically. So in this case, 2 metres sea level rise, so it might be 2150, say. And you can see half of Holland has gone. Well, I mean, they are building sea defences, but, and half of Cambridgeshire, East Yorkshire. And you can't see the little bit in London here, so I've plotted more details here. You'll be all right, Highgate, you're up a hill, but your supplies won't be. Yes. And of course, it's very difficult to predict what the impact on people and lives and livelihoods will be. This is from a project, I should have put in acknowledgements in here, sorry. It's from a project called the Avoid 2 project, and they make assessments about what these sort of changes in climate might do for people, and these are some of the results they get by 2100 if you have that worst scenario. Lots of people with not enough water, lots of people with too much water, 10 billion persons exposed to heat waves per year. Of course, that's more than the population of the Earth. What that means is some people are being exposed to more than one heat wave a year, several heat waves a year. and effect on the ecology and wildlife is quite bad as well. So, what can we do about it? What can we do? Adapt. This is, as some people suggest, that actually it's so expensive to try and do something about it, we better just learn to adapt. And indeed, we have to adapt in certain conditions. It's happening anyway, so we are adapting, the plants are adapting, and we'll have to adapt. But not everybody everywhere on the globe can adapt. This is a silly cartoon, but it's making the point. And indeed, it's the people who are living on the low-level islands in the Indian Ocean who won't be able to adapt because their homes will be underwater. So I think telling people to adapt is actually quite insulting. Do something else to compensate. So this is where boys with the toys have their fun. These aren't all silly. Some of these are silly. The idea is you do something else to compensate for what we've been doing already. So here's a silly one. Giant reflectors in space. Now, you may think that's science fiction. There are people in America working on how to do this. It's not one big reflector, it's lots and lots of little reflectors. And you keep launching them up from the equator up to some points between the sun and the earth. Carry on going, launching these things. And they can reflect sunshine to space and cool the planet. You can put stuff into the stratosphere, actually simulating volcanoes really. Little particles in the stratosphere. Again, you have to keep flying the stuff up there and putting it up there forever. I mean, if you want to keep the temperature down. Another way that's been actually experimented on, you put iron or other fertilisers for plankton in the ocean, and the fertilisation, more plankton, and they're sucking the CO2 out of the air and the water. Doesn't work. Here's a sensible one. Grow more trees. Trees take CO2 out of the atmosphere, so let's do some of that. Unfortunately, there's just not enough space to do enough. And then this is industrial carbon sequestration, where you suck the CO2 out of, say, fossil fuel power stations, and you store it in rocks or under the sea. And there's actually examples of that happening already. The Norwegian state oil company is already doing this with some of their emissions. But it's really not a solution. I mean, even if you did all of these things, it's just a fantasy, I think. So number 3, reduce the emissions. I mean, this is really the sensible answer. So here's the United Nations conference in Paris in 2015. This is called the Conference of the Parties number 21. And this all dates back to the Kyoto agreement. Actually, that was COP3, but it's been they have them every year, international United Nations conferences on climate change. And the big ones happen about every 6 years. And the previous big one to this Paris one was 2009 in Copenhagen. And we were all hoping that actually something would be agreed there, because there seemed to be, a lot of people working behind the scenes to get things agreed. It was a complete and utter disaster. They didn't agree on anything at all. Nothing was agreed. It was just awful. So when we were looking forward to Paris in 2015, we were thinking, let's hope they can agree something, please. And it was quite extraordinary. Quite extraordinary. I mean, remember, this is 4 years ago now. I'll come back to not quite good bits, but this is a good bit. It was a unanimous 195 countries agreement in aiming to keep global temperature rise to below 2 degrees above pre-industrial, and to try and limit it to 1.5 degrees. I mean, that was extraordinary that they got that passed. Done. Right. Now what we can do about it. This is a slight digression. Oh, okay. Yes, this is an important point. So the global temperature rise is actually dependent on the total amount of CO2 that's gone into the atmosphere. So you might decide that you want to stop the temperature at 1.5 degrees. You might decide you want to stop it at 2 degrees. You might say, oh, I don't really mind 4 or 5 degrees, actually. Oh, well, I'm happy with 10 degrees. Whatever temperature you choose, you have to stop, because it'll carry on going. It won't stop at 5 or 10, it'll just carry on growing. So you better stop now, actually, sooner rather than later. And the sooner you start, the sooner it'll happen. So I'm going into rant now, sorry, rant mode. I'll stop. I don't need to describe. It's just that the greater the greater the current emissions, the sooner you need to stop in order to get to any particular temperature level. So stopping, what does stopping mean? Stopping means that essentially there's going to be no net CO2 or greenhouse gas emissions into the atmosphere. So if there's some industries or sectors where it still has to happen, I mean, aviation is cited as one. You know, can we have green aviation fuel? I don't know. Other materials industries, cement's a problem. You know, all these ones. If they're going to carry on putting CO2 out, then we've got to try and find ways of taking it back in again. And I'm sorry about the poor quality of this picture. This is a wonderful organisation if you want to look at their website, but I just thought I'd identify three here. Direct air capture, so this is the where you're sucking it out of the industrial power stations and putting it underground. This is growing more trees, and this one is bioenergy. And this is with carbon capture and storage. And in fact, the Intergovernmental Panel on Climate Change has gone for this one in a big way, although it's still quite controversial. And what happens is you grow crops, and the crops take CO2, photosynthesis, they take CO2 out of the atmosphere. You then burn the crops, so you've got, say crops, plants, you've got the energy coming out of that, and then you capture the CO2 and store it. So you've got the energy and no net CO2. That's the idea. It does take a lot of land, and by crops is a bit of a misnomer because, of course, it's plants. And what will happen is may take land away from that should be growing crops. So there's all sorts of discussion about this, but it's an important thing to discuss. Right. So I talked about the good thing about Paris. I'm afraid this is the jog back to Earth. These are emissions into the future. Blue is what happens if we just carry on going as usual. The pink is what happens if everybody what they said they would do at the Paris meeting does what they said they would do. And they're not even necessarily going to do that. So you can see, you know, it's making a difference, but unfortunately it's just nothing like enough. The pale green is what needs to be done if we want to keep it below 2 degrees, and the green is what needs to be done if we want to keep it below 1.5 degrees. And this has become known as the emissions gap. So what we need to be doing is trying to pull these things downward. This is a more complicated picture, but essentially showing, it's a spaghetti diagram again of lots of different models, lots of different calculations of the same thing, about how to get to limit warming to 1.5 degrees. So the blue ones, you're peaking before 2020, and you're getting to net zero 2050, then you've still got negative emissions by the end of the century. The grey one, you peak later, you still get to net zero by 2050, but then you have to have more extraction later on. So it's you know, this is reality. This is a bit of a blame game. Perhaps this is emissions by country. I'll come back if anybody wants to talk about that. Obviously, China is the worst now. United States is pretty bad, but they're all varying with time, which is what these plots here are saying. And if you showed these per capita, of course, you'd have a far different blame game than just showing the global production. So there's a number of ways of playing this. So this is now more than 10 years ago. There was the Climate Change Act, and it set up a climate change committee, and it also established 5-year legally binding carbon budgets. So these are in law, and these grey blocks here are the legally binding carbon budgets that were set up in 2008. And the black is what's actually happened. So we have, this is the UK only, we have been declining in emissions. The little black dashes is where we were going when this plot was produced, and you can see it's sort of deviating from which is where we need to go, which is this one. But you'll also notice that this has got made in 2008 target at 2050 as minus 80%. And if you looked at the previous graph, it said we need to be at 0 by 2050. So this is it's good in the sense that the government was trying to do something. It's not so good in that they're missing the target. It's even worse that the target's not good enough. So Oh, that's a sort of slight deviation. This is a good bit of good news. This is energy capacity. This is not actually what's producing energy, but it's what we could do if it was all used to full capacity. And renewables overtook fossils for the first time last year, which was, way jolly good. Let's go. I'll come back to that other bit in a minute. But so this is the Commission on Climate Change Net Zero report, May earlier this year, and what the country needs to do. It needs to get zero gases by 2050, electricity, transport, buildings. I think in the UK, if we did insulating all the homes, that would do half of what we need to do. And then there's other suggestions like using hydrogen, which is a clean fuel, and you can use it for power, for heat, and you can even suggest putting it in the gas grid. Agriculture is another whole big issue. This is mainly to do with methane, not carbon dioxide, and this is ruminant animals releasing methane through their rear end and their front end. And there's, I was talking to someone that, yes, he knows more about it than I do. Ways of breeding livestock now where they actually produce less. You can also do things with waste management, so their poo sitting around isn't any good and you take it up and use it for something. So and I actually had a really interesting discussion with somebody from the National Farmers Union recently, and they were completely on board. They understand the problems and they're really thinking about what they can do about it. So it's not as if they're seeing this as the enemy, they're thinking of positive ways forward. And they also say we need to do this carbon sequestration and tree planting, etc., etc. So this is the government's independent panel on climate change. This is what we need to do. Theresa May, in her sort of passing her legacy, declared that we'd get to net zero by 2050, and she put that into law. Great. There's also, I put this at the bottom down here, is to do with climate finance for other countries. So this is all good, but here's the not so good. We are still subsidising fossil fuel companies, and if you read it, they'll say, oh, we don't receive subsidies. They do receive subsidies, but they're called other things. They're called tax something like this, or they're clever accountancy things. We have the highest fossil fuel subsidies in the EU. This is also shocking. This is export finance. Now, this is a perfectly decent scheme where the British government helps British industry to do stuff abroad, so it sort of gives them finance up front so they can get things going where the countries can't afford to do it themselves, which would be great if they were helping do clean infrastructure or whatever it is, or anything else, education, health. But what they're putting $2 billion last year into fossil fuel projects. So we have our wonderful Climate Change Act saying we're going to get to net zero, and at the same time we're building fossil fuel stuff in foreign countries. It's completely hypocritical. And here's another good one. It's not so good one. When we talk about our emissions, we're talking about what our activity creates. What it doesn't include is when, say, we import a lot of stuff from China and they've used a lot of CO2 in producing it. The CO2 from that goes onto their emissions, it doesn't come onto our emissions. So we're sort of getting it by proxy, we're cheating. And we are the biggest net importer in the G7. All these things are big worries. Plus, we might have a new Green Deal now. The parties seem to be talking about this, another major project. So let's hope something will happen. Also, as a sort of boring old physicist, I never thought I would spend time talking to people from the National Farmers Union, or indeed from people from the business sector. And I've had really interesting discussions with businesses. I've even been to the Bank of England, and it's absolutely exciting because their business, they're hard-headed. They just need to know what we need to do to get to where we need to get to, tell us about it and we'll do it, sort of thing. We just want a fair playing field. Carbon pricing is a controversial topic which I don't really understand properly, but the idea is, everybody's allowed a certain amount of carbon emissions and then it's equal. And there's a lot of private investors also investing in clean tech, which of course will bring jobs, clean jobs. So people can't work in the coal mines, they can work in nice, clean green jobs. And this is Mark Carney, a brother of Bank of England, so it may be that people don't like listening to old greenies like me, talking about this sort of thing, but they'll listen to the Governor of the Bank of England, and he has his climate-related financial disclosures, where companies have to, or offer to, put on their risk register all their risks to do with climate change. And then shareholders can read their risk register and they can decide whether or not to invest in those companies. And it encourages companies to, reduce their risks, obviously. Oh well. Meanwhile, the US, the good thing is, now I've forgotten his name, Jerry Smith Jones, Governor of California, has declared carbon neutral by 2045, and other American states too. So although US federally is not doing it, the individual states are. And another thing which I think is good is that the UK is going to host the next, I talked about the Copenhagen and the Paris, the next big one is going to be in Glasgow next year, and this is Claire Perry who's going to be heading it up for Britain. She stood down from government in order to do this. So I'll leave it here. This is too little, but you can see this 9 things you can do about climate change on the Grantham Institute website. I'll leave it there. Thank you.